Hello. Right, we are going to go through chapter 8 on page 95 of your textbook. Find it now. Okay, good. So, this chapter is all about how you can exert forces on materials and how they behave. It involves a few calculations, a few definitions, and a bit of understanding. So, I'm going to take you through this. So if you turn to page 96, I'd like you to read the section that talks about compressive and tensile forces. So do that now. Press pause. Okay, so you should have found out then the idea about compressive forces and tensile forces and understand the difference between the two words. And you should also know that when you stretch a spring, the amount of distance it goes further than its original length is called the extension. And you have done a practical about this, and you've actually ended up with a graph that you can see on figure 8.5 at the bottom of page 96. Okay, that is Hooke's law essentially. The first part of the graph, the straight line, the linear part of the graph, that shows the proportionality, that force is directly proportional to extension. Anything beyond that, so beyond point A, it doesn't follow that anymore, and that point A is called the elastic limit. It no longer behaves what we call elastically. It won't go back to its original length when you take the force away. Okay, now Hooke's law is something that we've discovered through the practical, and that is, like we said, force is proportional to extension, and that relationship is from the equation force equals the spring constant times the extension, which you can see if you read the section on Hooke's law. Read that now. Okay, Hooke's law is the definition at the bottom. You'll be asked to define that in the exam, and it says a material obeys Hooke's law if the extension produced in it is proportional to the applied force or the load. This is true as long as the elastic limit of the material is not exceeded. Everyone forgets that second point and then doesn't get 2 marks. Okay, if you wanted to practice these now, that's up to you, but you could have a go at the questions at the top of page 97. That should cover the basic knowledge so far. That's optional. If you want to do those, do them now. Press pause. Okay, lovely. Right, now springs. There's different ways you can investigate springs. You can connect them in series or you can connect them in parallel. If you connect them in series, like this, on that picture there, that just means that that force is over both of those springs and they'll both extend by the same extension. So if it would have normally have gone down by 2 centimeters, they'll both go down by 2 centimeters each, because that force is throughout the whole system. And as a result, your extension will be 4 centimeters. Okay? Whereas in parallel, connected in parallel, it becomes harder to actually extend those. So perhaps with 2 of the similar springs, the same as before, they would only go down now by 1 centimeter overall. Okay? It's all to do with what's called the spring constant. Now the spring constant, hopefully you got that from before, is essentially how much extension it does per newton of force. So it's basically in newtons per meter. How many newtons does it take to extend it a meter? So the spring constant of 2 springs in parallel, okay, that will be less than the spring constant of 2 in series, because the simple fact that it doesn't go as far. Okay, did I say that? Larger? Yeah, it takes a larger force to go down by a meter. So it's a larger force per unit distance. Okay? Right, on page 97, read a little bit about stretching materials, stress and strain. Okay, that practical right there is what we're going to do next lesson, all about stretching a wire using a force, and we'll be able to see what relationship we get there. So read about that, stress, strain, and turn over to page 98, and there's a couple of equations for strain and for stress. So some new definitions, and then carry on reading and read about what's called the Young modulus, which is basically the ratio of stress to strain. Okay, so have a little read of that, and I'll summarise that in a minute. So press pause while you do that. Thank you. Okay, so stress is basically the same units as pressure. It's a force divided by area, so the units are newtons per meter squared, and as you're about to tell me, the units of pressure can be abbreviated to the, oh yes, the Pascal. Now that is stress. Okay, it's a measurement of how much force is acting over a certain area. Okay, strain is a measurement of how much longer it has got compared to its original length. That's strain. Okay, so it's like a rate. It's like if it was 0.1, it's 10% bigger than its original length. So strain is a peculiar one because there's no units for that. It's units in meters divided by units in meters. So they cancel out and there are no units. And that is a very common question. What are the units of strain? The answer is there are no units. And just write that down, because that makes sense. There are no units. Okay, Young modulus is essentially how stiff the material is. So if it's got a high Young modulus, that means it's very stiff. What that means is, for a very large amount of stress, if you have a small strain, so large stress means a large force acting over that area, a small strain means it doesn't extend very far at all. Okay, so the Young modulus for a big stress and a small strain would be a very high number. That means it does not want to stretch, and perhaps as a result it's probably not very flexible either. So the Young modulus there is essentially how stiff something is. Okay, now again, Young modulus you can get from a graph that looks very similar to Hooke's law. If you plot stress against strain, if the area is constant and the original length is constant, which it will be, then essentially this is just a force against extension graph. So the idea is you get the same sort of graph, a straight line, and you can measure the gradient of the straight part, the linear part, and that will tell you the Young modulus for that material. It's a common exam question asking you to do that. Okay, so that's Young modulus, and you can see the Young modulus in the table on page 99. Have a look. The units for Young modulus are gigapascals. Okay, that's a billion pascals. They are always very high because it takes a large amount of force, essentially, to actually give it any sort of extension, because they're usually quite tough materials. Okay, but you'll see that is something you could look at a bit more in detail in the table for different materials. So if you wanted to, optional again, you can have a practice of the questions on page 99. There's some calculations in there, but again we'll be doing more of those in class. If you wanted to have a look and get ahead of the game, there's the questions on page 99. Press pause if you're doing them. Okay, 99. You can read a little bit about defining the Young modulus on the bottom right of page 99, and we will do an experiment to find the Young modulus of copper. Okay, the same as the experiment pictured on page 97. Okay, so that is Young modulus. Now the only other things in this chapter are a little bit about what happens when you stretch the materials. Okay, so it's basically how can you actually describe how things extend in terms of what glass, copper and polythene do. Okay, glass is a very brittle material, copper is what we call a very malleable or ductile material, and polythene or perspex is a polymer. It's a type of plastic, or you can think of some things like rubbers, things like that. They're polymers too. So you've got three different types of materials. So you'll have metals, you've got brittle materials, and you've got these polymers. So they do behave differently when you stretch them. And if you have a little look at the graphs, okay, on page 101, you can see anything that's brittle, you stretch it. Okay, the stress against strain is a straight line. There's no point where it goes beyond an equivalence like the elastic limit, okay, but there's no point beyond which it starts doing a strange deformation and it just snaps. So eventually it stretches a little bit, then it snaps. Directly proportional, then it snaps. Okay, things like ductile materials, you'll get to a point, and you'll see this with the experiment next lesson with copper. You get to a point where there's a linear part where the Young modulus you can work out from the gradient. Beyond that point is what's called the yield point, and then it gives a massive strain for a very small increase in stress. Okay, and that's the bit where you have what's called ductile flow, and it just very quickly becomes thin into a wire. Okay, that's ductile flow. And then the last thing is, say some polythenes, you get these peculiar strains where without very much effort you can stretch it quite a lot. And again, we'll see some behaviour about elastic a little bit later on for that. Okay, so there's stuff about stretching things, and if you want to do some questions on page 102, go ahead. Okay, last thing is basically elastic potential energy. You know when you stretch something, the work you do on that material to stretch it, the force multiplied by the distance, and as you stretch it, the distance will be the extension. Okay, that work done is essentially stored as elastic potential energy in that stretched material. Okay, so if you think about work done, it's force times distance. Alright, now force times distance, if you're looking at a force extension graph, okay, there's something that the graph can actually do. Now if you actually have a look at that there, you can see there's the graph, and it's the actual area underneath that graph there, which would be half base times height, half force times extension. That would be the area of that triangle. Now force times extension or force times distance is work done on that material. Now it's not fair to say that's the work done because that's the maximum force. So to find the average force, you just take the total force and divide by 2. And when you do that, force times distance is force divided by 2 times extension. Half force times extension. Half base times height, the area of a triangle. So on a graph of force against extension, the area underneath the graph is what we call the work done on a material, and that work done is stored as elastic potential energy. So you can actually read a little bit about that, and at the bottom of page 103 it derives that equation for you, which I've just said basically is elastic potential energy gained is the work done on the material, and you end up with the equation of energy stored basically is half times force times extension. Okay, and another way to actually do that, again, just think about the triangles. You just read through and it's there on the page. Last section is about work done in stretching or compressing a material. Now there's another way you can express it. Instead of saying half F times X, we know from Hooke's law force is the spring constant K multiplied by the extension X. And you can see at the bottom of page 103, have a go, see if it makes sense to you, just read it. And it just says, if you replace force with K times X from Hooke's law, then you end up with an expression which is half K times X squared. Or, if you want to call it that, half force times X, because we do know that force is K times X. So there's different ways you can express it, and your data booklet has them both. So you can use whichever one you choose. Okay, now if you wanted to, you can look through an example of a sort of question you might get asked on page 104 in the example. There's some more questions you can maybe look at if you want to practice now, okay, on page 104 to get ahead of the game. There's a nice summary as well of everything I've just spoken about on page 105 in a lovely blue box. So all those things, you should come to the lesson knowing those things in blue. So just go over them and be confident in them, because when you come to the lesson we're going to be doing a practical. I'll be using all these terms and then we'll do some calculations, and hopefully this video means that we'll spend more time practicing and less time listening to me, because guess what? Hot shots, you've already done it. If you wanted to, at any point, just remember in the book at the end of the section, page 106, you will find exam type questions. Okay, so there are 3 pages of those. Get used to the idea that they involve graphs. Okay, and in the exam question it will say use the graph. If it says use the graph, use the graph. Draw on it, gradients, lines, whatever you need to do to show you've used the graph. So there's some questions there you can always have a go at whenever you feel like it. Obviously there's questions we'll do in lessons, there's more sheets in your folders. Do whatever you need to do to understand this material. And just remember, you can do this yourself for all the other chapters too. And that, my friends, is called revision. Okay, right, I'm going to go and read this textbook before I go to bed. Because what better way to spend an evening than with physics. Until next time, take care of yourselves.